All right, so previously we were discussing explicit methods for solving parabolic equations like the heat equation. And as we saw, it's like this resulted in sort of constraints. It's like on the choice of spatial and temporal discretization in order to maintain stability of the method. So now we're going to consider implicit methods because as you recall, it's like from what happens in ODE systems, implicit methods oftentimes it's like allow you to have discretizations which are unconditionally stable or in some way have better stability properties. Okay, so we're going to look at parabolic sort of equations as before, but with implicit discretizations. All right, so as before, it's like we're going to study sort of a prototypical parabolic equation, which is the heat equation. So uxx is equal to ut, and t is greater than or equal to 0, and x is between 0 and 1. And then we have some initial data. It's like an initial time slice as well as boundary data. It's like for all time. So ux0, so this is the initial time, right, is g of x. Okay. And again, x is between 0 and 1. And then let's say that we're going to assume that the boundary is kept at 0 so for all time. So 0 u at 0 comma t is equal to u at 1 comma t equals to 0. This is for t greater than or equal to 0. Okay, so if you recall, it's like the way we had discretized this was to look at finite difference approximations of the second derivative and the first derivative, and then use this to rewrite the heat equation. It's like as an equation involving or relating points. It's like on the mesh. Okay, so you so in addition to discretizing the differencing, it's like you sort of essentially are trying to find approximations of the function value u. It's like at sort of a lattice. It's like in space and time. Okay. So let's consider some other finite difference discretization. Okay, so consider the following finite difference equation. Okay, so you have 1 over h squared v of x plus h comma t minus 2v xt plus v of x minus h over t. Right, so as before, this is a approximation of the second derivative term. It's like in space, which is here. Okay, and we want this to be equal to 1 over k v at xt minus v at x t minus k. Okay. All right. Yeah. So, and then this is, of course, it's like an approximation of the time derivative, if you will. Okay. So this sort of looks, not so different. It's like from the explicit method we considered before. It's like, but as it turns out, it's going to require a slightly different approach. It's like to trying to analyze it. Okay. So let's sort of see what is happening. So let's rewrite this. It's like in terms of notation we had before, where you think of having some sort of v on a lattice. Okay. So let's say that vij is equal to v, or is an approximation, if you will, of u at I times h, j times k, right? Something like this. Okay. All right. So with that in mind, we're going to rewrite this equation as 1 over h squared vi plus 1j minus 2 vij. Okay, and then plus vi minus 1j, k is equal to 1 over k, vij minus vi comma j minus 1. Right? Okay, so I'm going to leave that here at the bottom. Okay. Okay. So, as before, right? We can let S equals to k over h squared, all right? And then and rewrite this equation as follows. Okay, so you get minus S vi minus 1 comma j plus 1 plus 2s vij minus S vi plus 1j is equal to vi j minus 1. Okay, so let's try to analyze this. Okay, so so we let big V of j be equal to vij, sorry, v1j, v1j down to v and j. Okay. All right. So if you will, it's like, so if you recall, it's like the j corresponds to the time component, right? So this is basically, you know, it's like the discrete, the vector, it's like of approximations, it's like the solution at a bunch of discrete points, it's like for the jth time slice, okay? All right. So with that notation, you can then write the following. You can write this relationship in the following way, right? You can say that you have some matrix A, as before, Vj is equal to Vj minus 1. Okay, so this is the data from the previous time, and then everything else is the new time. Okay, and then A is this matrix of 1 plus 2s along the diagonal, and then minus s along this thing above the diagonal. It's like an minus s just below the diagonal as well. Okay. All right. So the difference, if you recall, is that in the other case, you had a matrix. The matrix was a little bit different, but you had the solution at the new time is equal to some matrix acting on the solution at the old time. Now you have that some matrix acting on the solution at the new time is equal to the solution at the old time. All right, so that's implicit, because then in order to figure out what the solution at the new time is in terms of the solution at the old time, you have to invert this linear relationship. Okay. All right. So so formally then, right, Vj is equal to A inverse Vj minus 1. Okay. And right, so as before, it's like you can sort of recurse this relationship. So that means that A inverse of A inverse, right, Vj minus 2, eventually you get that this is equal to A to the minus j V0. Okay. So, I mean, the reasoning is, and then it's like, so the stability condition for this then is sort of pretty much the same as, you know, it's like what we had done before, right? So, so because of this expression for the current solution in terms of the initial data, right? What you really want that is that the spectral radius, it's like of A inverse, right, is less than 1. So, so what we want that rho of A inverse be less than 1. Okay. Okay, so you can write this as, you can write A as the identity plus S times B, right, where the B matrix is equal to this diagonal of 2's, and there's a minus 1 up and lower piece here. Okay. All right. So as before, it's like you can figure out what the eigenvalues of A are. So the eigenvalues of A, right, are as follows. So lambda I is equal to 1 plus 2s 1 minus cosine theta I, where theta I is I pi over n plus 1, and I varies between 1 and n. Okay, so since lambda I are all greater than 1, right, the eigenvalues of AI, right, lie in the interval, the open interval between 0 and 1. So what this basically means is that irrespective of what S is, right, and S of course is the sort of discretization parameter which relates the spatial and temporal mesh size, right, irrespective of what S is, the method is always stable, right? So this is to say that the method is stable irrespective of S, and in particular irrespective of H and K. Okay. So this method is sometimes referred to as the fully implicit method. Okay, so this method sometimes referred to All right, so again, it's like conceptually it's very, very similar. Perhaps the one way to think about this is that this is a little bit like using forward versus backward Euler, right? Forward Euler is explicit, right? It has a stability condition. Backward Euler is implicit, right? And it's unconditionally stable. So conceptually, it's like it's like this kind of thing. It's like is very closely related to the properties of the underlying ODE method, if you will. Okay, and one way to sort of see this is through what is known as semi-discretization. So you could have derived, the implicit and explicit methods we had talked about for the heat equation by first discretizing in space using a finite difference in space, right? Then what will happen is that instead of a PDE, you end up with a system of ordinary differential equations. Once you have that, then you can discretize that system of ordinary differential equations using one of the numerical methods we had developed. It's like for ordinary differential equations. Okay, and so if you did central differencing to approximate the, so if you recall, it's like we were studying the heat equation. So if you have uxx is equal to ut, if you were to discretize this term here just in space, then you would have a system of equations. It's like in space, right, telling you what the values of the, it's like u, it's like at the various points are, okay, but its time derivative would still be continuous, and then once you've done the spatial discretization, then you can do the time discretization separately, and that would have given you exactly the explicit implicit methods we've been talking about, and that's a fairly standard way of discretizing PDEs. It's like is to first semi-discretize, first discretize the spatial derivatives, give you a system of ODEs, and then apply some sort of, it's like numerical ODE type method to the resulting system of equations. So anyway, let me just stop here for now.